Hello everyone, and welcome to the new tutorial series from EMBEDONIX, which will be covering programming STM8 micros from scratch. And from scratch, I mean we are not going to use any kind of external library or hardware abstraction layer things that you can find for example, STM32 micros. So we solely will rely on the datasheet from the ST, and also we will heavily rely on our brains. And to follow these tutorials, you need 4 things. The first is obviously some sort of evaluation board. The one that I have at hand, and it will be a benchmark for our tutorials, is this one. It's quite a generic evaluation board. There's pretty much nothing to it. It's only the STM8 S003 F3 P6 chip, which is a 20-pin micro with in T-sub package. And you will find a programming header. The USB port here is just for powering it up. The first LED is for the indication when the power is on, and the second one is named D2, diode 2 is the user LED. So for this first tutorial, we're going to figure out how we can set up the chip to blink this LED for us. Okay, that's the first thing you would need. And the next thing is, of course, a programmer. So you can get the ST-Link V2, something like this. I think this costs around 5 or 6 euros on eBay. That's the second thing. And since this series of tutorial is going to be on Linux, you will need to set up the development environment for yourself. The compiler that we are going to use is SDCC, or a small device C compiler. And the program to flash the program to the micro is called STM8 Flash. So I have a separate guide for setting this up in Linux. I will put a link in the description, and you can easily follow this tutorial, or you can watch the video to see how you can install the compiler and also write the generated codes to the micro. And that's pretty much it. So the other things that you will need is, of course, the datasheet of the chip. You can simply search for STM8 S003 F3 on Google datasheet, and you will find this file. And the other file you would need is the reference manual for STM8 S series. I will put a link in the description for these 2 documents, but anyway, you can find them yourself. So let's get started. Usually when you start with a new microcontroller, you want to see how you can set a clock to the microcontroller. And we're going to do that as our first step. So this is the datasheet. There's a lot of pages in here. I will not waste your time, and I will show you where to find this information. If you scroll down to page 33, you see that the clock registers are indicated in this table. And the most important register that we want to set is the divider. And you can see the clock divider register is at address 0x50C6, and of course this is a hexadecimal number, and its reset state is 0x18, or I think it will be 24 in decimal. So what does it mean? So we have to scroll up somewhere else on page 13, I think, because it should be indicated in the datasheet when the chip turns on for the first time, what will be the default clock speed. So on page 15, we will find this information, clock controller, and here it states that a startup clock is after every reset, the microcontroller restarts by default with an internal 2 MHz clock, and is HSI, standing for high speed internal RC oscillator, divided by 8. And since the maximum frequency of the internal clock is 16 MHz, then this will be 16 divided by 8 will be 2. So when you start up your chip, your micro, and you don't touch any of the clock registers, your micro will operate with 2 megahertz of clock. And for this tutorial, we want to operate the micro at its full speed, which is 16 megahertz, and we will see how we're gonna do that. So remember this, and let's go back to the clock register. We want to set this reset state value to something else, and the register is this one. So without further ado, let's start coding. Okay, I'm going to make a new folder. I will call it STM8 Blink. I will go inside this folder, and I will write a new file named blink.c. Okay. I'm just going to introduce our main function, return 0, and this is the base for our work. Okay. Now we need somehow to tell the compiler when the code runs, edit the content of this register to the things that we want to it to be. So for that, I'm going to use a simple define. So I want a dereference to a pointer to a unsigned character, and I will give the address. It is 0x. Don't mind the leading zeros. 50C6. So. And here, oh, I forgot to name it. I will define this as CLK for clock, div R or division R or divider R for the divider ratio. And when our code starts, if we set this to 0, then the internal RC oscillator will work at its maximal speed, which is 16 megahertz. Set clock to 16 megahertz. Okay, and this will cause our chip to work at 16 megahertz. And the next thing is we want to know how we can configure the I/O pins of the micro. So I have to show you this again. On this board, the diode number 2, D2, is connected to PD3. It means port D of the microcontroller, and pin 3. So remember that we have to configure the PD3 port pin to output, because every port in a microcontroller can be as an input or an output. So we want to drive this LED high or low. So we need to set up this pin of this port to output. So let's see how we can do it. We will go back to the datasheet, and in the register addresses we want to look for port D. Yeah, it's somewhere in page 31. It says port D, and you see there's quite a lot of options for port D. The first one is the port D data output latch register. So if you set a bit in this byte to 0, then the output will be low, and if you set a bit high or 1, then the output will be high. And the other thing that we have to control is the control register 1. It will tell the micro to configure the pin as push-pull or open drain or all kind of those stuff. So to get more information about this, you need to refer to the reference manual, and this is explained in page 106. Okay, let's find it. Yep, 105. Yep. Okay, you see the general block diagram of GPIO pins. So these two transistors or MOSFETs are for the push-pull. So when you set low, then it's connected to ground, but when it's high, then it will output the current to the pin or outside world. So let's see how we can set it to push-pull mode. Okay. This is the configuration summary. If the data direction register, that's something that I have to tell you again, is the PDDDR, is the data direction register. It will tell the pin to be output or input. So we want it to be output, so we have to set it to 1. And here we wanted to set it to push-pull. Then we have to configure this in the control register number 1. And I will show you in the code how you can do that. So, but the most important thing is that we have to get the a definition to the pointer to this address in memory. So I would say define port PD underscore ODR or output data output latch register. Again, unsigned car and the address which is 50 0F. Then we need to the pointer to the DDR or data direction register. Define PD DDR unsigned car 0x 5011, and then the control register 1. For this, for blinking the LED, we shouldn't touch the control register 2, but in the next tutorials we will see what it is useful for. So CR1 unsigned car, and the address for CR1 is 0x5012, and I have a typo here. Unsigned car, yeah. It looks nice now. So let me indent this for you so you can see it more clearly. Okay. Yep. So first of all, we want to set all the pins to low. So when the chip starts, nothing is going to go outside the pins. So I would say ODR equals 0x00. Turn all pins of port D to low. And we want to set the data direction register for the pin 3 of this port to output, so we have to set it to 1, and we can accomplish that with a simple bitwise operation. So we can OR it with 1 shifted by 3. So this will result in the byte of this register to look like this: 8 7 6 5 4 3 2 1 0. Oh, 1 0 is extra. Oh, sorry, I had to start from 7, of course. So 7 6 5 4 3 2 1 0. Okay. So as you see, the result of this assignment will be this. It means the third pin of the port should be output, because the pins of the port are started from pin 0 to 7. And the next thing is we want the control register to tell the microcontroller to set this pin to push-pull. We want to do the same thing like this. PD3 is now output. PD3 is now push-pull. So this is the effect of these assignments. So let's see where did I bring this push-pull from the reference manual. And as you can see here, it says if you want to set it to push-pull output, then you have to set the DDR bit to 1 and CR1 to 1, control register 1 to 1, and CR2 to 0. And because the control register 2 is already 0 when the chip starts up, we don't need to set it. So let's go back to the code. And that's pretty much it, but we need a while loop so we can tell the microcontroller to turn off and on this pin for us. So I'm just simply going to say PD ODR. I will XOR it with itself. Okay. So this will alternate between this and this. So it will turn on the third pin, and for the next loop it will turn it off. Then we need kind of a delay. And for the delay, I'm going to introduce a variable here. I would say unsigned int, unsigned long int, DL for no CL. It doesn't matter. Delay loop. And very important thing that you have to remember is that int is 16-bit in STM8. So it's really different from your desktop because this is an 8-bit micro. The integer will be 16-bit, so it means your maximum value will be 4096 if you start counting from 1, or 4095 if you start counting from 5. But sorry, I have to say this is the unsigned int, 4095. And the normal int or signed int is also 16-bit, and it will be from minus 2000 something to 2000 something. I don't know the exact numbers, but that's why we have declared our loop counter variable as unsigned long. So we have, I think, a 32-bit value. So let's make a loop for DL equals 0. DL is smaller than, I don't know, I will put just some random numbers. And I will tell you later how you can achieve a very exact delay function. Let's say for now 18,000 and DL++, and in this loop we do nothing. Okay, and that's pretty much it. If we run this code, we hopefully can get a blinking LED on our board. So I will plug in my micro, and I will try to compile and flash the program to the chip and show you the result. So let's save the file. I have connected the micro to my PC, and let's compile the our work. And as I told in the beginning, we are using to use SDCC, and you just call it like this. You write the command of the compiler, and then you give it the name of the source file. Then you should pass these arguments, because it's the way to tell the compiler that we need this program to be compiled for STM8, and which is -L STM8 and followed by -M STM8. And we want the output file to be in Intel hex format. That's the output format that the STM8 flash can work with. And to do that, you should use the switch -out fmt ihx, and we want to name our output file to be blink.ihx. Okay, so we have one warning. It says at line 26 we have unreachable code. So let's visit the code again, but before that let's try to list the outputs. You see that the SDCC has generated these files for us. So this REL, RST, SIM, and all kind of formats is just the intermediate files to generate this IHX, which is your final output of the application compiler. Sorry. So let's try to get rid of this warning on line 26. And I think line 26 is this. Yeah, and it's quite obvious because we have a endless loop here, so this return will never be reached. So the best thing is to just cut this line and let it go. And let's compile again. And this time we have no warnings and our output is here. So now let's try to flash the program to the micro. And for that I'm going to use STM8 Flash. And as I told you in the beginning, I have a separate tutorial for installing SDCC and STM8 Flash and how to use them. You can check the link in the description and see that video for yourself. So STM8 Flash, then we need to say or compile or programmer is ST-Link v2, and the product that you want to program for is can be given by -p switch STM8S003. And the -w is the file that we want to write to the micro. So in this case will be blink.ihx, and we have flashed it. And let me take some video for you from the chip. Okay, I'm going to bring the file again, blink.c. So we have to increase this loop counter. So let's make it something like 50,000. And let's compile again and flash again. Now this time it's a bit more obvious, the blinking, but let's even increase the delay even more. So let's make it 150,000. And let's compile and flash again. Now this time it's much better. So that's it for this tutorial, and the next one I'm going to tell you how to implement a very exact delay routine and how we can refactor these definitions in a header file